This is Swathi, working as Assistant Professor in Institute of Aeronautical Engineering in the Department of Electronics and Communication Engineering. Welcome to today's lecture. In this lecture, we'll discuss about the rectifiers with capacitive filter, and we'll see the effect of capacitive filter on the ripple factor of the rectifier output. So, as we already studied the rectifier and the various types of rectifiers like half-wave rectifier, center tap full wave rectifier and bridge rectifier, and we have seen the output of each and every rectifier. So the the major operation of rectifier is to convert the alternating current into direct current. That means it has to convert AC to DC. But the output of rectifier still consists of some AC components, so which we need to remove in order to get the pure DC. So here the AC components present in the DC, that is why the output, DC output of a rectifier, that is why the rectifier output is called as pulsating DC, where we have AC components also present in that output. So we use at the output of the rectifier another circuit, which is a filter. So filter is an electronic circuit which is used to remove the AC components present in the output of rectifier. So here the filter can be constructed by the combination of components such as resistors, capacitors and inductors. So as you already know the properties of capacitor and inductor, so where the capacitor allows AC components and blocks the DC component, because the reactance offered by the capacitor for the DC components is infinite, and hence it blocks the DC components and allows the AC components. Whereas the inductor allows the DC component and blocks the AC component. So using these properties of capacitor and inductor, and in combination with resistor, the filters are designed such that the filters will be able to remove the AC components present in the output of rectifier. So we are going to discuss the rectifier with capacitive filter. So here, what is a capacitive filter? So the capacitive filter consists of a capacitor connected in shunt with the load resistor. So we can also call this as RC filter. So this filter is always used at the output of the rectifier such that it is able to remove the AC components present in the output of rectifier, such that the amount of ripple will be reduced, such that the ripple factor will be reduced. So here, this is the half-wave rectifier circuit with capacitive filter circuit diagram. So as you all know, the half-wave rectifier consists of a single diode, and here the output of the rectifier is connected to the capacitor, which is connected in parallel with the resistor RL. As it is connected in parallel with the resistor RL, this capacitive filter is also called as shunt capacitive filter. So why we have to connect this capacitor in parallel? Why not in series? So here, as we all know that the capacitor allows AC components, the capacitor allows AC components, whereas DC components are blocked. So if you connect the the capacitor in series like this, so what happens? The output of rectifier consists of AC plus DC. So whereas we require only DC component, where I have to remove the AC components present in the output of rectifier. So if I connect the capacitor like this in series with the load resistor, as a capacitor allows the AC component and blocks the DC component, so DC components will all be blocked at the input of the capacitor, and no DC component reaches the load resistor. So that is why we should not connect the capacitor in series with the load resistor. So where if we connect the capacitor in parallel, what happens? Actually, this is the other end of the capacitor which is connected to the ground. So here, the input to the capacitor consists of AC and DC. As a capacitor offers less reactance path for the AC components, all the AC components are flowing through the capacitor. That means will be appeared across the capacitor and will be connected to the ground. Whereas the capacitance offers very high reactance to the DC component. So that is why the DC component will not be allowed into the capacitor and they will be entering into the load resistor. So that is how the AC components all will be grounded, whereas the DC component will be appeared across the load resistor. So that is why always the in case of a filter, always the capacitance should be connected in parallel. So that is why this capacitive filter is also called as shunt capacitive filter, such that all the AC components are grounded and the DC components will be appeared across the load resistor. Now let us see the operation of this half-wave rectifier with the capacitive filter. So what happens? As you all know, the output of rectifier, that is a half-wave rectifier, is having only positive half cycle, whereas the negative half cycle is removed. So here now this output is coming to the input of the capacitor. So we know that whenever the current flowing through the capacitor, the capacitor charges to its maximum value, and when no current is flowing through the capacitor, it will discharge the charge stored by the capacitor through a resistor. So here, during the positive half cycle of input voltage, what happens? The diode D is forward biased and it is short circuited. So there is a flow of current through the diode and through the capacitor. So as there is a current flow through the capacitance, so the capacitor will be charging. And the capacitor will charge up to the maximum value of input voltage, that is Vm. So once the capacitor has charged to its maximum value Vm, now the voltage across the capacitor is equals to Vm. Now after the positive peak, the input voltage is going to decrease to become negative half cycle. So that means now after the capacitor has charged to plus Vm, then the voltage applied to the anode will be reducing as the input voltage is going to the negative half cycle, and hence the potential at anode is less when compared to the potential at cathode, because the cathode is connected to the positive terminal of the capacitance, which reverse biases the diode. That means once the capacitor has charged to maximum voltage Vm, the charge across the capacitor will reverse bias the diode, and hence the diode now will be open circuited. So due to that, there will not be any current flowing through the capacitor because the diode is open circuited, and hence now the capacitor will try to discharge through the load resistor R. So that is what I have shown in the output waveform. So up to the maximum voltage, the capacitor, the blue line shows the output of the, or else voltage drop across the capacitor. So the capacitor will charge up to Vmax. Once it is charged to maximum voltage, it will try to discharge because the diode is open circuited, because the voltage drop across the capacitor reverse biases the diode, and hence it is open circuited. Now the capacitor starts discharging. That means losing the charge stored by it. So it will discharge to its minimum value. So this is the discharging of capacitor. And the charging is happen when the diode is forward biased. When the diode is forward biased, the resistance offered by the diode is RF, which is very less. And hence you already know that the time constant T of the capacitor is equals to R into C. As the capacitor is charging through forward resistance of the diode, so the charging time constant is very less. Whereas the capacitor is discharging through the load resistor, where the load resistor is very much greater than RF, and hence the discharging time constant is equals to RL into C. So that means when we compare the charging time constant with the discharging time constant, so the charging time constant is very much less than the discharging time constant because the capacitor charges through the forward resistance of the diode, whereas it discharges through the load resistance. So when we compare the forward resistance of the diode and load resistance, the RF is very much less than RL. So the charging time constant is very less when compared to the discharging time constant. Means what? The time taken by the capacitor to charge to its maximum value is less when compared to the time taken by the capacitor to discharge to its minimum value. So that is shown here. So that is why here the charging period is very less when compared to the discharging period. This is the time taken by the capacitor to discharge. So this is very high when compared to the charging time constant. So here, this is the operation of rectifier with capacitive, half-wave rectifier with capacitive filter. So the capacitor, as I told you that capacitor provides high resistive path to the DC components and low resistive path to the AC components. And hence, all the AC components will be passed through the capacitor and will be grounded, and the DC components are opposed by the capacitor and will be reaching the load resistor, and hence we can get the DC components at the load resistor output. So that is what. So during the conduction period of the diode, the capacitor charges, and during the non-conduction period, the capacitor discharges through the load resistor. So here, this is the waveform of the half-wave rectifier with the output waveform of the half-wave rectifier with capacitive filter. So this is the input. So during the positive half cycle. So here, one thing you have to remember. So whenever the applied voltage is greater than the cut-in voltage, then only the diode starts conducting. So that means after V gamma only, the diode starts conducting, and hence there will be a current flow through the capacitance, and hence the capacitance starts charging. So this is what V gamma. And next, after reaching to its maximum value, the diode gets reverse biased and it will be discharging. So again, once the input voltage is again greater than the cut-in voltage, again the capacitance charges and then discharges. So this is the output waveform which we can observe at the capacitive filter. So here, still if you observe this waveform, you can identify that still there are some AC components present in that. So that is why again we need to find out the amount of ripples present in the output of the filter. So for that, we need to calculate the ripple factor. So here, for calculating the ripple factor, what I am doing is I am taking the output waveform. So this is my output waveform. So here now this time period, let us consider this time period as capital T, and this is T by 2, okay, and this is 3T by 2. So this is the output waveform here. Now here let us consider this is a discharging time period. Let us indicate this one with T1. Let us indicate this one with T1. So here, if you consider the charging time period, which is very much less than discharging time period, and here this is the entire period of this period of the waveform. So if you consider this the difference in the charging time constant and discharging time constant, we can say that the time period T1 is approximately equals to T by 2. So approximately equals to T. Approximately equals to T. Whereas the charging time period plus discharging time period is equals to T here. T1 plus T2 let us consider. So as a charging time constant is very less, so we can say that the entire period of that is equals to discharging time period, which is given by T1. So here T1 is approximately equals to T. So now we know that the capacitor charges and discharges exponentially. So as a discharging means it is losing the charge. That means exponentially decreasing. The voltage or else the voltage across the capacitor during the discharge time period or else during the discharge is represented with Vc of t is equals to, here it is discharging from Vm. What is the maximum value here? Up to Vmax it will charge, and once it is reached to Vm, it will start discharging. So from Vm to minimum value, it is discharging. So that means in order to find out the ripple factor, first we need to find out the maximum value and minimum value. Okay, minimum value of the ripple voltage. So for that, what we are doing, we are considering the discharging period and we are representing the voltage across the capacitor during the discharging time. Discharging time is represented as e power minus t by RC. So here the discharging is happened due to the load resistor. So that is RL into C. So Vm into e power minus t by RC. So where discharging time period, I have told you that Vc of t is equals to Vm into e power minus t1 by RL into C. So why I have considered RL? Because a capacitor discharges through the load resistor. So we are considering RL into C. So now, as I told you that T1 is approximately equals to T because the charging time constant is very less. So in that case, the voltage drop across the capacitor Vc of T can be given by Vm into e power minus t by R into C. E power minus t by RL into C. So this is the equation. So here we know that Taylor series expansion. So what is that Taylor series expansion? So here we have exponent function, that is e power x. According to the Taylor series expansion, it can be expanded as 1 plus x square by 2 factorial plus x cube by 3 factorial plus and so on. So here, as I told you that, and we need to consider one assumption, that is time constant RL into C is very much greater than time period T. If we consider this, then T by RL into C will be very much less than 1. So that means here we can say that if it is the case, if RL is very much greater than T, then this denominator is high. In that case, exponent factor of very less value. So that means it will give you a small value. So that means x value will be very less, and hence if it is the case, then we can neglect all the higher order terms. Then e power x can be written as 1 plus x, because x is very less. So x square will be further less. That is why I can neglect all the higher order terms, and e power x can be approximated as 1 plus x. Then if it is e power minus x, we can write it as 1 minus x. Now from this expansion, Taylor series expansion, we can write the voltage drop across the capacitor Vc of t as Vm into 1 minus t by Rc. 1 minus t by Rc. T by RL into C here. So now I can write this one as Vc of t is equals to Vm minus Vm into t by RL into C. So this is the equation for the voltage drop across the capacitor during the discharge time period. So here this is that means when we are considering the discharging time period, the voltage drop across the capacitor is becoming V minimum, and hence as at time t is equals to t1, the voltage drop across the capacitor Vc of t becomes V minimum, and hence I can represent V minimum is equals to Vm minus Vm into T by RL into C. This is the minimum voltage across the capacitor during the discharge time period. Now, as I told you that in order to calculate the ripple voltage, the peak to peak voltage of the ripple, peak to peak value of the ripple voltage, we need to calculate the maximum value and the minimum value. So we have found that minimum value as Vm minus Vm into T by RL into C. Now coming to the maximum. So Vmax, which is the maximum voltage drop across the capacitor, is equals to Vm. That means during the charging time constant, the capacitor charges to its maximum value. So that is Vm. So now the ripple voltage peak to peak. Ripple voltage peak to peak can be given by, so we can calculate the peak to peak value of the ripple voltage as Vmax minus V minimum. So that is why we can write it as Vmax minus V minimum, so that we can find out the peak to peak value of the ripple voltage. So where Vmax is equals to Vm minus V minimum is Vm minus Vm into T by RL into C. So here, now if I expand this one get cancelled. So I can get it as Vm by T into Vm into T by RL into C. This is the peak to peak value of the ripple voltage. So we can also write this one as Vm by F into RL into C, where inverse of time period is nothing but frequency. So this is the maximum voltage across the capacitor. So here this is, and we can let us have the okay. This is the peak to peak value of the ripple voltage. So now before going to calculate the ripple factor, first of all we are going to calculate the DC value of this this waveform. The DC value of this waveform can be given by Vmax. Okay, that is Vmax minus maximum value minus average value of this ripple voltage. So that is VR peak to peak divided by 2. This is, so always you know that the DC value can be calculated by from the average. So the DC value of the, or else average value of that ripple voltage can be given by Vmax minus VR peak to peak divided by 2. So this is the DC voltage, DC value of the ripple voltage or else voltage across the capacitor. So now here we already found that VR peak to peak, which is given by Vm by F into RL into C. So here from this expression, so always you remember that ripple voltage, as we are using a filter, ripple voltage will be of the order of millivolts, whereas Vmax will be of the order of volts. So as it is of the order of millivolts, I can neglect this one. So I can approximate this VDC as Vm. We can approximate this VDC as Vm. So and hence substitute this Vm is equals to VDC in this case. Then VR peak to peak becomes VDC by F into RL into C. So already we know that the DC current flowing through the load resistor is given by IDC, which is equals to VDC by RL. So the ripple or the peak to peak value of ripple voltage in terms of DC current flowing through the load resistor is given by IDC into FC. IDC into FC. So this is the peak to peak value of the ripple voltage. So we have found the value of this ripple voltage, and then a peak to peak value of the ripple voltage, and already we know that VDC is equals to Vm minus VR peak to peak divided by 2. So here we know that the formula of ripple factor is VR RMS divided by VDC. What is VR RMS? This is nothing but RMS value of ripple voltage. RMS value of ripple voltage divided by average value divided by average value. So here we need to find out the RMS value of the ripple voltage. So for that I am considering the waveform of ripple voltage. So here this is my waveform, and on x-axis we are taking time period and on y-axis we are taking the output voltage. So here the waveform, if you observe, so it is just looking like a sawtooth waveform, because I already told you that the discharging time constant, the charging time constant is very less when compared to the discharging time constant. If we consider the diode to be an ideal one, so in that case RF is equals to 0. That means the charging time constant will also be equals to 0. That means at an instant the capacitor will charge to its maximum value. At an instant, once the input is applied, the capacitor charges to its maximum value. So if you observe this waveform, it just looks like a sawtooth waveform. So that means we are going to calculate the RMS value of this waveform. So where each cycle is having a period of T. So T, 2T, 3T and so on. So we want to find out the RMS value to this waveform. That means we need to find out the RMS value to this sawtooth waveform. So for that, I am taking one assumption. What is that? Here I am removing the offset. So that means I am removing the DC level so that the waveform can be seen like this. The waveform can be seen like this once if I neglect the offset voltage. Okay, so this is the waveform by neglecting the offset voltage. This is plus Vm and this is minus Vm, and the period it is T, and this one is T by 2, this is 3T by 2 and this is 2T and so on. So we are taking, so this is a waveform by neglecting the offset voltage. So here if you observe this waveform is symmetrical about T by 2 period. So that means if you find out the RMS value for a period of T by 2, that will give you the RMS value for this entire waveform. So now we are going to find out the RMS value for this waveform. So how can we find out the RMS value for this waveform? So we need to write down the mathematical expression for this one. So as it is a sawtooth waveform, the mathematical expression for this one, V of T, can be written as Vm minus 2Vm by T into T. So this equation is valid for a period of 0 less than T less than T. So this is the mathematical expression which is representing a sawtooth waveform, which is representing our ripple voltage. So here, now let us consider if T is equals to 0. What is V of T? If T is equals to 0, V of T is equals to Vm plus Vm. Okay. At time T is equals to 0, we have plus Vm. And at T is equals to T by 2. What is the maximum? What is the voltage at the capacitor? So that is Vm minus 2Vm by T into T by 2. So this T get cancelled. So 2 get cancelled. Vm minus Vm. So that is 0. At T by 2 we have 0. And if you consider T is equals to capital T, then what is the voltage? V of T is equals to Vm minus 2Vm divided by T into T. So this one get cancelled. So minus Vm. That means at T we have an amplitude of minus Vm, and at T is equals to 0 we have an amplitude of plus Vm. At T is equals to T by 2 we have an amplitude of 0. So that means this equation is valid for a period of 0 to T. So now we have the equation. Now we need to find out RMS value of that. So that is Vrms square, that is root mean square value. As I told you that this waveform is symmetrical about T by 2. We need to find out the RMS value for a period of T by 2, and the formula for that is given by 1 by T by 2, 0 to T by 2, V of T square dt. V of T square dt. Now as you know the equation of that, so just substitute that equation in this 0 to T by 2. V of T is given by Vm minus 2Vm by 2 Vm by capital T into T whole square dt. So here Vm is a constant value, so I am taking it out, so that it is 2 Vm square by T integral 0 to T by 2 1 minus 2 by T into T whole square dt. Now it is in the a minus b whole square formula. So just expand this one. 2 Vm square by T integral 0 to T by 2 a square, okay, minus 2ab, that is 4 into T by T, 4T by T. Next, plus b square nothing but 4 by T square into small t square dt. Now apply the integration. So 2 Vm square divided by 2 integral 0 to T by 2. Integration of constant is T minus this one is integration of T is T square by 2. So it becomes minus 2T square by T plus integration of T square is 2 cube by 3, T cube by 3. So 4 into T cube by 3 into T square. Okay. So already we have applied integration. So now apply the limit 0 to T by 2. So here after applying the limits 2 Vm square by 2. So it is T by 2 minus 2 into this becomes after substituting the limit we'll get it as T by 2 again here. It is T by 2 plus T by 6. So this is after applying the limits. So now I can write this one get cancelled. So Vrms square value becomes 2 Vm square by T, Vm square by T. So now here the remaining thing what we have here is Vm square by 3. Vm square by 3. So this implies that Vrms value is equals to Vm by root 3. If I consider, if I multiply and divide this one by 2, 2 Vm by 2 root 3. So here Vm plus Vm, this is nothing but V peak to peak. V peak to peak. So Vm plus Vm minus of minus Vm, that is equals to 2 Vm. So we can represent it as V peak to peak divided by 2 root 3. So this is the RMS value of the sawtooth waveform which we have considered. Now let us approximate this one, or else let us equate this RMS value of the sawtooth waveform with the ripple voltage. So and hence as we know that the ripple voltage is same as sawtooth waveform. So the RMS value of ripple voltage, that is VR RMS, is given by VR peak to peak divided by 2 into root 3. VR peak to peak divided by 2 into root 3. So this is the RMS value of the ripple voltage, which is just like a sawtooth waveform. So now we have got the VRMS value. So now let us find the ripple factor. Let us find the ripple factor. As you all know the formula of ripple factor, which is represented with gamma, that is VRRMS divided by VDC. VRRMS divided by VDC, where VRRMS is given by VR peak to peak divided by 2 into root 3, where you know the VDC value, that is given by Vm minus VR peak to peak divided by 2. This is the VDC value. So here, as you all and now substitute, already we have the formula for VR peak to peak, which we have derived as VR peak to peak value is given by VDC by FRL into C. VDC by FRL into C, or else Vm by FRL into C. Just substitute that in this equation. So Vm by 2 root 3 F into RL into C divided by Vm minus Vm divided by 2 into 2 root 3 F into RL into C. VR peak to peak value is given by Vm by F into RL into C. So here we won't get the 2 root 3. So Vm divided by 2 into F into RL into C. 2 into F into RL into C. So here now we already know that RL into C is very much greater than T. RL into C is very much greater than T. So that means it is very high value. In that case, I can neglect this one. So in that case, this equation becomes Vm by 2 root 3 F into RL into C. As I have neglected this one, so I can have only Vm in the denominator. So I can get, it can get cancelled. So the ripple factor half-wave rectifier with capacitive filter is given by this 1 by 2 root 3 F into RL into C. So this is the ripple factor of half-wave rectifier with capacitive filter. I hope it is clear. Now, coming to the center tap. So what we have done, we have taken the output waveform of the half-wave rectifier with capacitive filter and we have derived the equation for ripple factor. So that what we have seen that VR peak to peak half-wave rectifier is given by Vm divided by F into RL into C, or else we can also write this one as IDC divided by F into C. IDC divided by F into C, or else we can also write this one as VDC by F into RL into C. And we have also derived the ripple factor, where the ripple factor formula we have got it as 1 by 2 root 3 F into RL into C. So these are the formulas that we have to remember for half-wave rectifier with capacitive filter. Now let us see the full wave rectifier with capacitive filter. So in the full wave rectifier also we have two types, center tap full wave rectifier and bridge rectifier. Now let us see the circuit diagram of center tap full wave rectifier with capacitive filter. So this is a center tap full wave rectifier and we have the capacitor which is connected in parallel with the load resistor, and this entire circuit represents the full wave rectifier with capacitive filter. Now what happens? So here in full wave rectifier, the current flows through the load resistor during both the half cycles. That means during the positive half cycle, diode D1 conducts, and during the negative half cycle, diode D2 conducts. And hence we can say that there is some current flowing through the capacitor in both half cycles of the input. That is during positive half cycle and during negative half cycle. Let us see the output waveform of this full wave rectifier. So during the positive half cycle, diode D1 conducts. During the negative half cycle, diode D2 conducts. When the input voltage is equals to cut-in voltage, then the diode gets forward biased and the current flows through the diode, and hence the current will be flowing through the capacitor, and hence the capacitor charges. Once the capacitor has charged to its maximum value, as the voltage drop across the capacitor is more when compared to the voltage applied to the anode, and hence the diode D1 will be reverse biased and D2 already is in the reverse bias condition. So there will not be any current flowing through the load capacitor, and hence now the capacitor will be discharging to its minimum value. And again, during the negative half cycle, what is happening? Diode D2 is forward biased. So that is why there is some current flowing through the capacitor. Again, the capacitor charges. And again, capacitor discharges. So as we have both positive half cycles of output for a complete cycle of AC input signal in the full wave rectifier, there is the capacitor is charging and discharging for each positive half cycle and also negative half cycle. So this is the output waveform that we can see. That means what I said, during the conduction period of diode D1, the capacitor charges, and even during the negative half cycle, diode D2 conducts, and due to that, the capacitor again charges. So again here also we have to consider that the charging period of the diode capacitance is very less when compared to the discharging period, because the charging is happening due to the on diode, that is forward bias diode, which offers very less resistance. And discharging is happening due to the load resistor, which is very high when compared to the forward resistance of the diode, and hence discharge time constant is very high when compared to the charging time constant. So that is why you can observe this waveform here. The charging time period is less when compared to the discharging time period. Now, let us see the bridge rectifier with capacitive filter. So this is a bridge rectifier. Again, the capacitance is connected in parallel with the load resistor. So here, again, the same output appears across the load resistor, same as the center tap full wave rectifier, because during the positive half cycle, any of the two diodes among the four diodes will be conducting, and the remaining two diodes will be non-conducting. And during the negative half cycle, the other two diodes will be conducting, and the two diodes will be non-conducting. That means in either of the half cycles, current will be flowing, and hence the capacitor charges and also discharges. So this is the capacitive filter with bridge rectifier with capacitive filter. Now, we'll also try to find out the ripple factor of the full wave rectifier with capacitive filter. So for that, again, what we need to do, we need to take the output waveform, so which is having charging and discharging time period. Okay, so here now let us consider this is during the positive half cycle. Just a second, sorry. So during the positive half cycle and negative half cycle, there is some current flowing, and hence a capacitor charges and discharges. So here, this is the charging period of the capacitor, discharging, charging, discharging. So here this is T by 2, and this is T, this is 3T by 2. So now let us consider this is my discharging time period. This is my discharging time period. Let us consider this as T1, whereas my charging time period is T2. Okay, so here as I told you that T2 is very much less than T1. So whereas complete period is equals to T1 plus T2. So as it is very less, we can consider it as T, whereas the complete period is equals to T by 2. Means during a half cycle only, the capacitor charging and discharging. So that means here T1 is now equals to T by 2. This you have to remember. Okay, so now the capacitor discharges at a time T is equals to T1. This on x-axis we have to take T time period, and on y-axis this one. So again, in order to calculate the maximum ripple voltage, peak to peak value of the ripple voltage, so we need to calculate the maximum value and minimum value. So in order to calculate the minimum value, I am considering the voltage across the capacitor during the discharge time period is given by e power minus t by RL into C. Whereas at time t is equals to T1, Vc of t is equals to V minimum. Is it or not? At time t is equals to T1, the capacitance is discharged to its minimum value, that is V minimum. And hence at time t is equals to T1, we have to assume that Vc of t is equals to V minimum. And time T1 is equals to T by 2. Just substitute that in the equation. Then V minimum is equals to Vm into e power minus T by 2 into RL into C. Because T1 is equals to, so in this case, V minimum is equals to Vm e power minus T1 by RL into C, where T1 is equals to T by 2. So, whereas Vmax is equals to Vm. So now we are finding out the ripple voltage peak to peak. VR peak to peak. So VR peak to peak, that is the peak to peak value of the ripple voltage, is given by Vmax, maximum value minus minimum value. So where we have already, and here before that, according to the Taylor series expansion, we can approximate this one as Vm minus Vm divided Vm into T divided by 2 into RL into C, because here again 2 RL into C is very much greater than T by 2, very much greater than T by 2. So that is why I can approximate that e power minus T by 2 into RL into C as Vm minus Vm by T into RL into C. So Vmax is Vm minus Vm plus Vm into T divided by 2 into RL into C. So here this becomes Vm into T divided by 2 into RL into C. So this is VR peak to peak. So coming to the VDC. So already we know that the DC value of ripple voltage is given by Vm minus VR peak to peak, VR peak to, just a second, VR peak to peak divided by 2. So here already we know that ripple voltage is of the order of millivolts, and hence I can neglect this one. So VDC is approximately equals to Vm. So I can write this one as either Vm divided by 2F into RL into C, whereas Vm can be written as VDC divided by 2F into RL into C, where IDC is given by VDC into RL, and hence I can also write this one as IDC by 2F into C. 2F into C. So that means VR peak to peak can be given by VDC divided by 2F RL into C, or else IDC divided by 2F into C. So this is VDC. Sorry, VR peak to peak. Now again similar to that, we need to find out, after finding the R peak to peak, we have to find out the VR RMS, because the ripple factor formula is RMS value of the ripple voltage to the average value. So in order to find out that, we are considering the waveform, so which is just like a sawtooth waveform. Just a second. So we are assuming that the charging time constant is 0, because the forward resistance of the diode is 0. So this is the voltage V of t, which is just like a sawtooth waveform, where the period of this one is t by 2 and t 3t by 2 and so on. So now in order to, this is Vmax, okay, so that is Vm, okay. So in order to calculate the RMS value, what I am doing is I am assuming that I am removing the offset, so that the waveform can be approximated like this. As you all know that the period is t by 2, so this will be t by 4. So this is V of t. So this is time period. This is 3t by 2. Okay. So this is t. Okay. So here now, if you observe this waveform, this is plus Vm. So what I have done, I have just removed the DC offset. This is minus Vm. So this waveform is symmetrical about t by 4. So now if you calculate the RMS value about t by 4, that will give you the RMS value of this entire waveform. So Vrms is equals to 1 by t by 4 integral 0 to t by 4 V of t, V square of t dt. We are finding the RMS value, root mean square value. So that is 4 by t integral 0 to t by 4. Now coming to the V of t equation. So the equation for this V of t is given by, so I am finding out the equation for this one. So which is Vm minus 4Vm by capital T into T, and this is valid for a period of 0 less than or equal to T less than or equals to T by 2. Okay, so this is the equation. Now, by substituting this one in this, so that is Vm minus 4Vm by T into T whole square dt. And after expanding this and applying the integration, you will be getting VRMS value as VRMS value as Vm by root 3. So now again what I am doing, I am multiplying and dividing this one by 2. So in this case what you will get, V peak to peak divided by 2 into root 3, because 2 into Vm is nothing but the peak to peak value of this waveform. So now let us approximate this with the ripple voltage of the full wave rectifier with capacitive filter. So that is why VRMS, that means the RMS value of the ripple voltage will be given by VR peak to peak divided by 2 into root 3. So now we know the formula for ripple factor is gamma is equals to VR RMS divided by VDC. So we already know the value of VR RMS. We already know the value of VR RMS, which is VR peak to peak divided by 2 into root. And VDC value is, we know that Vm minus VR peak to peak divided by 2. Now the gamma is equals to VR peak to peak divided by 2 root 3 and Vm minus VR peak to peak divided by 2. So now substitute VR peak to peak value, which is given by Vm by Vm by pi. Just a second. VR peak to peak value is Vm by 2f into RLC. Vm by 2 root 3 into 2 into f into RL into C divided. So this is the value of just a second. Sorry. So VR peak to peak is 2 into FC into RL. So this is VR peak to peak value. So now just substitute this in the gamma equation. So Vm divided by 2 FC RL into 2 root 3 divided by Vm minus Vm divided by 2 FC into RL into 2. So here we already know that RL into C is very much greater than T by 2. So I can neglect this term. So and hence gamma becomes Vm divided by 4 root 3 RL into FC divided by Vm. This one get cancelled. So gamma becomes 1 by 4 root 3 FC into RL. So this is the formula for full wave ripple factor of a full wave rectifier with capacitive filter. So here, and we already know that VDC, VR peak to peak is equals to VDC divided by 2 FC into RL. So these are the formulas that we have to remember. So this is the ripple factor of the full wave rectifier with capacitive filter. So this is about the rectifier and its operation with the capacitive filter, and we have derived the ripple factor equation for half wave rectifier and full wave rectifier with capacitive filter. Now let us see the advantages of capacitive filter. So very less number of components, because only a single capacitance is needed for filter out the AC components present in the output of rectifier. And the low ripple factor, hence low ripple voltage. So even we can observe the output waveform, the ripples are very less, and hence the ripple factor will also be reduced. and it is suitable for high voltage at small load currents. So this capacitive filter can be applicable for the application where we have high voltages at small load currents. And coming to the disadvantages, ripple factor depends on the load resistor. So as the load resistor changes, ripple factor changes. So that is major drawback, and not suitable for variable load as ripple contents increase as load RL decreases. So as we have seen the formulas, so ripple factor is a function of load resistor. So if we have variable load resistor, so the ripple factor will be changing. If load resistor decreases, the ripple factor will be increasing. So, and coming to that, as it is depending on the load resistor, so we can say that regulation is poor. Regulation, we already know that the definition of regulation, we should not observe any change in the output voltage even for the variations in the load resistor or load current, but it is happening with respect to the capacitive filter. So that is all about the rectifiers with capacitive filters. I hope it is clear to everyone. Thank you once again.
Like, share and subscribe. Hit the bell icon for more updates.